I've sent the link. I've sent the materials into Telegram group, so you could check it out if you want to do things with me. Then that's the first thing. The second thing is my small introduction. My name is Vladislav Vencherenko, and so I'm a curator of MSAI program, and I'm working as a computer vision team leader in self-driving cars startup. So I know something about computer vision in different areas, in different situations, starting from research and ending in production. So we will have a course in computer vision. Yeah, and we will start from practice and then proceed to theoretical part, which will be ready, I think, during weekend. And from there, you will know more theoretical things, how images are formed, why is it so, and so on. But today, I want to focus, on the practice, and here it is. Let's see. We will do computer vision in Python, and our first seminar. Let me restart my notebook. First, we will use Matplotlib and NumPy. I think it's not a big deal. It's not. Hello to Andrei Mikhailovich. We'll start from computer vision libraries in Python. In fact, doing computer vision usually requires some kind of high performance stuff, but since we are doing data science and artificial intelligence, but not image processing, that's why we could use Python. But if you think about something production level, I think it's feasible to concentrate on C++. And the first library to speak about is OpenCV. It stands for Open Computer Vision, and it's written in C++, as I said, and in fact, de facto, it's a standard for image processing, because OpenCV is, I guess, the most used library in computer vision. Everyone uses, everyone forks it, everyone do something around, and all baseline solutions are from OpenCV. It contains very large library and for any situation in computer vision. If you want to read image, write image, read video, write video, process images, you could do stereo matching, you could do many things. It was released in 2000, and currently it has 57.5 kilo stars on GitHub. They have this beautiful site, with AI competition of current year. Also, they have courses, tutorials, documentation, but it's still written in C++. Don't forget. That's why documentation is kind of old-fashioned, and I think you will get familiar with it. And I think here in documentation page, the most, I mean, during our course, I hope you will visit this site of documentation, not only once, but many times, and let me explain some key features of it. I will zoom it in. And the first one is here is a version of OpenCV that you could choose. You could check out your version and put it here to read actual documentation. The second field that is very useful is search. It really works. For example, let's uh, let's look at documentation for IMRead, which stands for image read, and here's some more constants from imread, and it's kinds of colors that we could read with. And here we go to documentation. You see, it's a large page on some module. And here we got C API, ISGlue, macOS guide, and so on. And many functions were in C++ style. It has signatures, names of parameters, and so on. Also, we got this detailed description, and for now we are interested in IMRead, and here there is two types of documentation. The first part of it is for C++ API, which is default for OpenCV, and its namespace CV, usual C++ double colon, and imread function with file name and some flags. And in Python, we got a separate documentation line, and it says CV imread file name, and it returns some red val. Then we got description, we got parameters, and for example, flags here stands for imread modes, which is this table, and we got interface for Python here as well. So if you are surfing on these pages, so get familiar with it. If you know C++, you could check out headers for this enums and so on, as well as source code is open source, as you could guess from description. So the interface for reading image is very simple: file names and flags. Nothing to fear. And here is the formats. It's plenty of formats: WebP, TIFF images, JPEG, BMP, PNG, and everything, almost everything you want. Yeah, not so user-friendly for fancy, smoothly Python developers, but still you could get familiar with it. At least they did beautiful landing part. And they're celebrating their 20th university. Okay. Here we got some courses on computer vision, part 1 or 2 with deep learning and OpenCV and so on, and plenty of tutorials, as well as GPU accelerated computing with OpenCV. So let's continue. How to install it in Python? We could use pip install here, and it's written as OpenCV Python. It's enough to do this way. It will work, and it will install the package that you could import with CV2 signature. CV2 stands for open source build, because original OpenCV builds are not so friendly to install, and they it's not an official build of OpenCV CV2. I mean, That's why it's 2. But don't care, it works well, everyone uses it. It's related to Python community who just made it more user-friendly. And usually for OpenCV, I use this command to install OpenCV Python headless. And headless stands for the thing. OpenCV has high, so-called high UI interface. This thing, high-level graphical user interface. This is a thing from OpenCV, and in fact, it's a very buggy and it's a very ugly interface for drag bar windows, demonstrating images, demonstrating some ROIs and everything. But it's I'm not I suggest you not to use it in any circumstances, because it's very buggy and ugly. If you want to use some graphical interface for Python, I suggest you to use Matplotlib for visualizing in Jupyter notebooks or saving these images to disk. Or if you want some graphical application, you could either use PyQt or some web application. It's kind of my suggestion for graphical interfaces. So speaking about version of OpenCV, we could check it. And yeah, I did not. Okay, I won't install it because I have already done it. And let's restart. So we import it and we here see 453. And we could check it if we want in documentation. So let's move on. Let's read some image. It's called Lena PNG, and what we get is we get a NumPy array. Yeah. What we get is a NumPy array, and let's check it. Yeah, it's a NumPy array with the data type of uint8, as we see here, and some data. We will find more about it a bit later. And that's the first library. And if you don't know what to use, I suggest to use OpenCV. First, because it's a very widely used, the most widely used library in computer vision. And the second reason for that is when you when you use OpenCV interface, you could easily transfer it to C++ and make your pipeline more production ready with a couple of hours of rewriting, or giving it to your friend who is C++ developer. And that's the baseline for computer vision. Moving on to Python, we could speak about the second most used library, and it's called Pillow. Its real name is Pillow, but usually it's referred as a PIL or Python image library. It's a separate development. It has separate development process from OpenCV, completely different. It's written in Python mostly and in C++, so low level part in, sorry, in C, in pure C. in contrast to C++. It's originally written in 1995 and restarted as a pillow. First, it started as a Python image library, and it's used all over for example, Linux distribution and other open source distribution like BSD, Arch, and so on to process images in these operating systems. Yeah, initially it started as a PIL or Python image library, but then authors of the original project abandoned it, and the group of enthusiasts taken this project, forked it, and called it Pillow. That's why it's called Pillow. So we install it as a Pillow here. Yeah, initial release 1995, and then GitHub Star Scene is 9.1K, and it's a less less easier to move it to production pipeline because Pillow is only for Python and not for anything else. We could, after installing, and yeah, please don't install it as a PIL, because I guess you will have a warning that PIL is a wrong thing, or maybe you will install the required thing like Pillow, but I don't recommend to do that. Install it as a Pillow. So after we import Pillow, we could import image class from it and as well open some image. And let's write it to Pillow EMG, and Pillow EMG will show it. Since it's a separate class, it's not a NumPy array because it's a Python library. It's not bindings from another language, from another library to Python. That's why it has separate class, its own class, like an image. Yeah, and still we has shape. Oh no, we don't have, but we have size and so on and so on. Usually it's in uint8 as well, because that's how it's stored by default on disk. We will speak more about it in lectures. And here to default way to get a NumPy array from Pillow image is just this way. Just to provide it to a constructor of NumPy array, and you will get the same array. For example, we could check that it is all close to OpenCV EMG. Oh no, that's not true. Nice thing. Let's look at it. And then shape, and then type. Yeah, that's how it goes. Here, what we have here is shape of 512 to 512 to 3, and here we got yeah, the same thing. Why is it different? Okay, I don't know in fact, but that's a strange thing. Or if we do this way, it's still false. Nice thing. Okay, I will check out how it works, how it happens. So okay, and yeah, it has a bit different format of images. So let's move on to the third library, the top three libraries for image processing in Python, and the last one is scikit-image, and it's some cousin of scikit-learn. That's a bunch of scikit something, because they have a community for scikit surprise, for recommendations. Yeah, scikit-learn, everyone knows it, and scikit-image. And scipy is from the same community, as I remember. So the language here is Python, but scikit-image depends on Pillow. So under the hood, it uses Pillow. So it's not a low-level library, it's a high-level library over Pillow, but it has lots of extended functionality and lots of extended transitions, approaches, and so on and so forth. And speaking about, yeah, let's first go deeper into scikit-image. They have their documentation as well as, for example, gallery, as well as documentation, sub packages to do different things. Yeah, some examples like scikit-learn do, and so on. You could check it out for different tasks. Yeah, they have examples, many examples, and so on. Scikit-image package is interesting because it has, as I said, extended pool of algorithms, and it kind of mimics OpenCV imread function with their IO module, and they as well return they return NumPy array as well as OpenCV do. Does, yeah. Let's check it out. It's a NumPy array, also 512 to 512 to 3, and you indate nothing to be surprised. Let's check all close, and for example, with OpenCV EMG, and it's already, yeah, I think it's just the wrong settings for all close, because they should be all close. Or let's make it this way. Oh yeah, open. Yeah, I know the reason. I know the reason, because OpenCV reads image with a BGR format. Yeah, it OpenCV image in BGR format. You know, RGB, it stands for red, green, and blue. That's the channels of colored image. And here in OpenCV, by default, image is red in BGR format. I don't know exact reason. I guess it's a historical one. So if we make, yeah, to make this way, if we do things like this, yeah, we still got fail. Okay, okay. Mhm. Or if it, yeah, that's a success. Yeah, it's so close. Scikit image, and pillow image. Yeah, that's not surprising because scikit image uses peel under the hood. But yeah, here if we put OpenCV image and we will do will inverse channels. No, we don't have good result. Okay, okay, I will check it later. So the next thing is, yeah, let's go to images and doing something with images. First things first, and here you can see the most famous computer vision image. It's called Lena, or it's called Lena. And these photos, this girl have has a separate Wikipedia page for this story. And in fact, it's an image that is used as a standard test images, as a standard test image since 1973, and it is a Swedish model who has a photo session for Playboy magazine, and the story is like guys who did image processing as they get the first file from their disk, and that was a file of Playboy image. And this phenomenon has a separate side with a full image because that's a crop of original image, and the original image is as follows, but it's not all of this. It has a lower part. You could check it out here by link. I won't open it because it's a kind of Playboy content for 18 plus auditory. So, you know this story. Let's move on. We'll use this picture just as a reference of image with different colors, with different shading, and with foreground, background, and anything we need. Speaking about images, as we already seen, by default, images are stored as Unit 8 numbers, and they change from 0 to 255, and usually we want to move it to forward to float 32, usually for neural networks, but that will be further material, usually in image processing, and I will tell more about it in theoretical part. Yeah. Yeah, someone reading that Peel and OpenCV has RGB and GBR. So float 32 is not used in image processing. I will dig into reasons about that in lectures. And float is only used for neural networks. So most of the time, for the first part of the course, we will use Unit 8. Also, we have three channels. First, it's a number of channels, but by default, yeah, in fact, by default, we should do this thing. And first, it's width, then height, and then number of channels. That's how it's stored in memory, and that's why we we've seen this 512 to 512 to 3 channels is the last one. That's a default for classical image processing and for all the basic libraries. And for neural networks, because you already know about convolutional neural networks, convolutional layers, they require channels to be the first dimension, and then width and height. That is made because convolutions in neural network have to work with continuous data. That's more convenient for neural networks for convolutions. But for image processing, for historical reasons, channels is the last dimension. So we could check data type and magnitude for this image and move it to float and check that data type is different and amplitude is different too. So now let's move on to the next notebook, to practical part. Yeah, that's what we have here. It's an image from unit data and float representation. It differs a bit, as you see, but it's not crucial. Then we have colors. I will as well speak about it more in theoretical part, but for now we should know that RGB exists. It has 3 channels, as I said, for R, for G, and for B. It's in fact B. Okay. Then we have, and if we represent it as a grayscale image with only 1 channel, we'll have such a thing. Then we have different color encodings. There are many of them. For example, let's check this. We have, for example, YCBCR color space. And here we get channels for such an image. And for you to know more about these spaces, we could look at this table. Here is a color space section of Wikipedia. And here we got all the color spaces that is known, that is widely known. Yeah, I will zoom it in just to make it more clear. Yeah, and what we will use is RGB for most, and it's a 1 color space to note. XYZ is another kind of theoretical color space. Then we will know about SMIC, and we will know about HSL and HSV. All the others are not so widely used. They are used for some more specific purposes, or they have some historical meaning. Yeah, but main one for illuminating is RGB, and that's the main thing here. So different color spaces. Okay. Let's move on to images, and let's see how it goes. If we try to do such a thing, let's imagine that we have not 0 to 225, but we have lesser number of colors. For example, we want to use not uint8 images, but uint4 images, and that's why we want number of colors and number of magnitudes to be reduced. For this situation, we could do the following thing. We could cluster our colors from image. So what do we have? We have an image with channels, and we have a values for each color at each pixel. And these values could be represented as a histogram, and we will use it today a lot. And here, what can we do if we have limited number of colors. For example, if we want to binarize our image, that's what we will get. And yeah, the algorithm is as follows. We reduce quantization, having an image and target number of colors. Then we make it a flat array, and then we apply k-means algorithm for these numbers. Then we use labels and centers to reformulate our colors. Because we use centers of labels and create a new image with a lesser number of colors. Then we plot it just like we usually do in our computer vision things. Yeah, here we apply it to one channel. It could be done to other channels as well, and we will have different images. For now, only one channel for simplicity, and increasing number of colors will give us more and more detailed image. And here we have centers of clusters. Let's make the following thing. Yeah, I think that's enough. Yeah, I will remake it. It's for k-means. Yeah, that's what we have. And for example, let's make a colored image out of this thing. And okay, then reduced R. Then we will set number of colors, for example, to to 2, and then we will have G, and then apply number of colors, and reduced image final is np.stack of these three. Oh, we have to reshape it. We have to stack it over minus on the last axis, and that's what we will get if we reduce colors for 3 channels. Let's make it with 3 channels, for example, and it gets better. And if we apply, for example, 10 colors, it gets better and better. Yeah, and here we have full colored image, and here we got only 10 colors for each channel. You can see here that, yeah, it's let's make it bigger. Yeah, you can see these levels of colors that appears, and that's related to our clustering. Here here's how it goes, and gradients become not so nice looking thing. And here you can see at her face and so on. That's kind of thing that happens when you use JPEG file format for saving images many and many times. Because, for example, PNG format is a lossless format. We store full representation of unit 8. But if we use JPEG format, it's a compressed format, and it could be compressed with different quality. That's why we could get such an artifacts in JPEG as well. Okay. And if we, here we have quantization levels for this colored image. The next thing is histogram. And as I mentioned before, if we put all the colors to our scale and make a histogram out of it, we'll end up with something like this. And there are plenty of things we could do with histogram. Here you can see how it's calculated. We get a flattened version of X, then binarize it to integer bins, and then we return counts and levels. Okay, that's for Lena. Then why should we care about this histogram? We could use it to make image processing algorithms. For example, we could move some part of this histogram to some direction. Let's make it. For example, we have this low contrast image, and we can see, histogram, and haven't defined it. Okay, we have a low contrast image. Here we can see not so many details, not so many things, and that's how histogram looks like. Because Lena is very nicely post-processed, this picture has kind of a flat histogram, but this low contrast image have very concentrated histogram. And what could we do with such a histogram? Scikit image already has three things to do with it, to deal with it. And it's adjust gamma, and we will know more about this image processing algorithm. Apply logarithmic function and equalize histogram. The first thing is histogram equalization. What do we do here? We, for example, we count the minimum value for the image, then we create linear transformation that moves this point, the leftmost point of the histogram, to 0, for example, and rightmost to 255. And under the hood, everything is made. Then we compilate it into uint 8 to get it with right values of colors in channels, and that's what we end up with. Different thing, we could see anything. We could see here is a river with the color of a river, and here is some green parts, which is I think some maybe avenues or maybe parks, and here we got something like port or something like docks, and so on. And that's how histogram looks like. It's not that that dense as we see in Lena image, because made it we made it less we made it from original one, where we have discretization worse than everything. But also we could apply additional post-processing to have this histogram, to make this histogram more dense and not to have these empty spaces between each color. But that's a different algorithm. And speaking about image processing, it's all about manipulating images to make it kind of better for the task that we want to solve today. And that's a basic method for working with histogram. Also, we could make such equalization, or we could apply the same algorithm for some part of the image, or we could move the balance to another point, and so on. So these are manipulations with histogram. The next thing is gamma correction, and we will use such a photography of some person in water. And what do we do here? Gamma correction is another typical operation on images, and here what's the change? What the function do we apply to our original image? We power it to gamma, and then we increase it in gain and move to uint8 to get ourselves in this space. Then let's try different gammas from 1/4 to half and to 2, and we'll draw everything. First, we apply gamma correction with some gamma, then we will look at histogram and so on. Just to remember original image, yeah, and if we apply gamma correction, we see that, yeah, here we got original image with a histogram like this, and as I mentioned, when we apply gamma correction, we pull some pixels here, and here we have, in fact, lower contrast, but we change the view of image. And if we apply gamma with 0.05, we got this image, and we can see, well, at least I can see the background in more details compared to the original image, because it's not crowded here. It's more have more space here. That's why our eye could detect such differences. And that's a very important thing in image processing, because everything depends on how we represent our image, and how we try to visualize it, because one image, as we already seen from low contrast image, everything depends on this representation, because if we represent it originally, it's a very low quality photo, and if we equalize diagram, we got the photo that we could get something with. Yeah, as I mentioned, yeah, that's the original image, and if we apply gamma with power of 2, we pull everything to the left. So Another thing is logarithmic correction, and that's kind of the same thing. Here we got gain as well. It's a linear characteristic, and here we got logarithm 1 plus 6. Since x here is from 0, so we need to add 1, not to get logarithm to minus infinity and start from 0. And we kind of flatten our histogram. And we will apply it to a Fourier transform of our original image. And as we see here, let's for example, let's look at histogram as well. As you see, we see some better details in this photo, because in the original image, we see almost nothing, and here we see some details. And let's look how it looks like in terms of histogram. Okay, and then we have to plot it. Okay, it's I get histogram, and yeah. Oh, we have the okay. Right. Okay. We gotta we have the type of plot 64 and maximum values. Yeah. Okay. Okay. And then we could yeah, and that's a histogram for this value. We got a histogram of only one value, but if we first apply logarithmic change, then we do the following thing. uh, just log. We already imported it. Why don't you have it? Yeah. Okay, I guess from binarization we get the image wrong, but if we do it this way, oh, it's still the same. Because we binarized it here. Okay, let's make it this way. Yeah, that's the thing. And when we do the following thing, yeah, we got this one. So as you see, after logarithmic translation, we move this spike from only one value to some represent to some different values. And for example, let's okay, to have, here we get denoising. Okay, so to make it more practical, let's make the following thing. Let's choose 05 change in gamma correction, and let's equalize this image histogram. What do we need to do here is to get original image of a swim, then apply gamma correction with the coefficient of 0.05, and we have such a photo, and then we want to more discretized image with more equal histogram, and what do we need to do is it's a unitate still, and since we have this histogram, let's for example, let's set all values from 0 to 25 to 25 to cut the histogram from left part, and let's cut histogram from right part by, for example, 175. Yeah, and let's look. That's a swim corrected original. Another next step is all pixels, which is less than 25, becomes 25. And another transform is all pixels that is greater than 175 becomes 175. Then let's look at what happened. Yeah, and it's still BGR. Yeah, it's still BGR. It's an ugly thing. And yeah, we did the following thing of sim upgrade. Yeah, we kind of binarized this white part of the spectrum, and now let's apply equalization of histogram Mhm. And show it one more time. That's what we get. We get a higher contrast, but we have lost some of original values, but we, for example, achieved the better better visibility of detailed objects, and that's how all the uh, transformations of images work. Okay, okay, I think that's enough for this seminar. We have, yeah, we have filtering with Lena. Yeah, okay. Let's start the next notebook of seminar 2. I think it's no reason to hesitate. Uh, as I mentioned, before, we have three libraries for image processing, and less known and less used is image.io, which is another base for scikit-image. That lays under the hood in scikit-image. So we in fact use imread from scikit-image. That's the same thing. Okay. Then we will use this Lena photo as well, but again in grayscale, and let's add some random noise to this image. So we have original Lena and we have noisy Lena on the right. Let's look at what could we do with it, and we could measure peak signal to noise ratio, and it's oh, I have a wrong version of scikit-image. Okay. Okay, it was here, but now it's not. Well, okay. In fact, what do we need to do? We need to apply a convolution, and that's the route where convolutional neural networks takes their start from. We apply average filtering, and how do we apply it? Like in usual convolutions, we take some pattern, then we normalize this pattern, and we apply just convolution from SciPy signal, like we did on starting seminar of convolutional neural networks. Roman wrote, which lives in used in Adobe Photoshop, Lightroom, etc. Oh, the question is, what libraries are used in Photoshop, Lightroom, and other programs? Usually such big companies as Adobe, they have their own libraries for image processing, and it's more, it has some advantages over OpenCV, just like, for example, some corporations such as Yandex, such as Microsoft, such as other companies have their own instruments, for example, for big data, their own instruments for CI/CD and everything. And since Photoshop, Adobe's main business is imaging, and everything connected with it. They have whole bunch of tools by their own. So in fact, basic algorithms are the same, but they are more advanced. And we will speak later about color spaces, for example, and we have traditional RGB standard, and it's like a not so big figure. And for example, Adobe RGB space, like color space, it's a much bigger space that
Vladislav,
contains more and more pictures. Yeah.
just small note. You can replace PSNR by peak signal noise ratio. I sent you in chat. It's in the new version. It was updated.
Yeah. Okay, thank you. Why don't you define? Yeah. Okay, thank you. Yes, we got peak to signal to noise ratio of 20. That's a big number, and yeah, we could deal with it. Okay. As I mentioned, yeah, averaging summation and just convolution do, well, it does something. That's here we have a small grained noise. Here we have more kind of blurred image, but we have it with more, it's more convenient for human's eye. Yeah. Another thing here is if we apply average filtering for different number of times, we will have different number of PSNR values, and it will decrease and decrease. That's because we go more for averaging and blurring and blurring. That's not what we want. And in image processing, it's always a trade-off between, for example, a high contrast and high details, and zones with the same coloring, with the same with the same intensity. Okay, another thing is Gaussian filtering, and I think that's one of main approaches in computer vision. The thing here is we want to apply some Gaussian kernel instead of, for example, square kernel, because it concentrates more on the center and connects it with some more details in mind. And let's apply it. Let's get it. Yeah, and that looks like more common blurred image. If we compare it with our first filter, it's a more kind of detailed picture. I think in this magnitudes of kernels, it's not very big difference, but still it differs a bit. And signal to noise ratio also decreases as we convolve more and more, but we lose our initial image also more and more. What else? Another girl is Barbara. She has the same history with Lena, but it's more like follow up for the first picture. And the thing here is these parts of cloth because it has a very nice pattern to flicker, and with this pattern, we could apply different, for example, applying convolutions, we will get very different results for this image. And another image is Laplace filter. Yeah, but I think, yeah, we'll need, I think, more theory here for such a filtering. But after applying Laplacian filter, we will get these patterns very well seen, as you see here, for example. And we could also sharpen this image, because we will get a kind of more detailed part of the image, and we could make it more visible for us. That's how we apply this change to image and get sharpened Barbara. And unsharpening is done in a different manner, like in a contrasted manner. That's we see here, we removed all those lines from her genes, yeah, as well as we removed most of the these sharpened regions from this cloth. Yeah, that's how Laplacian filtering works. And if we apply it to Lena, then we will have such a picture. We see that detailization of this part is increased. Yeah, and Fourier. Okay, I think let's move on to Fourier. Yeah, that's how we process images. In fact, in classical computer vision, we have plenty of transformation, of standard transformation. I think they are counted 10 to 15 usually, something like that. And applying them one by one, we could move to the image that satisfies us better and better. And that's another thing for doing augmentations, for example, because all of you, I guess, have neural networks, convolutional neural networks in mind, and all these features, all these things is for you to first augment data, and second, not to apply neural networks for everything, because not more than a week ago, I did an interview to my team. So the guy who applied, he moved to our office, and we had a dialogue, and I asked him, how do you augment the data if you have some data sets of images? And he said, well, I will take a GAN, like a generative not adversarial, like a GAN neural network. Okay, then I will those GANs that changes gaze direction. There are models which takes your pictures and move your head, like spin it a bit. And he said, I will do that. Yeah, adversarial. Yeah, okay, adversarial. Yeah. So I said, do you have an easier way to do that? And he said, no, it's kind of no way to do that, but I know about, for example, perspective transform, which provides almost the same functionality, but with a classical thing. Another thing, last year I read the thesis of one bachelor at MIPT, and what he did was he taken open source data set and he trained neural network to apply Gaussian blur for image, but with a convolutional neural. He did like an unconvoluting on Gaussian kernels. Like you have original image, then you do some Gaussian convolutions like blurring, and he unblurred the image. But we know that classical approaches could unblur the image really well without any neural networks, and that's what happens every time with people. That's why I think all these methods are very relevant for us. We have more of them on the next two notebooks, and we will speak about it in the next seminar. I think that, for example, Gaussian unblurring will go well to our conversation. And for now, let's go to Fourier domain transformation. All of you know the Fourier transform, I guess, and that's a sinusoids, cosine, and so on. What do we have here? We could apply NumPy fast Fourier transform to our image, and that's what we will get. A real part and imaginary part. That's two parts of an image. That's relevant because those Fourier functions are valid for two-dimensional space of an image. That's why we could apply it really well. And what could we do? The simplest way we could do is just mix some things together. For example, what we could do is look at spectrum of Lena. That's in fact not very informative for you, but still it exists. For example, the next thing to do is we could apply only some frequencies to our image and restore it. It's very similar to PCA, but PCA makes it with linear models and with directions. But here, and I guess you have seen what picture look like after we apply SVD transformation. We do it in machine learning basic course. And here we do the same, but in domain of Fourier. And that's what we got with one frequency, and that's what we have with 5 frequencies. You see, if you know who the Lena is, you will know that is her. And if we apply 10, we already see the face and this hat and everything. And if we apply 12, we already see almost everything. But since we used Fourier transform, we see these lines of periodical grid from starting from each border. And that's how JPEG compression worked some time ago, before JPEG 2000, because on that point they enhanced their algorithm. But in early web, we seen these pictures because of such a compression. And yeah, that's another way to make something with images, it's handy for example, if you want to get rid of low of high frequency components from images, for example. That's what it could get practical meaning. And the final thing is we mix. We have Mona Lisa and Albert Einstein, very famous pictures 1 and 2, and we apply magnitudes from Einstein and phase from Mona Lisa on the left, and vice versa on the right. And here we see that phase is more about image structure than magnitude, but magnitude stands more for not coloring, but for magnitudes. Not coloring, but intensity. It's called intensity. So I think enough for today. Some of the ways to process images for you, and I think we'll continue next time with another approaches to processing classical processing of the images. When the first lecture? Yeah, I think it will be ready by the end of the weekend. Yeah, and it's about colors, it's about image forming, it's about basics, and it uses physics and all the basics. Then we go to classical imaging theory, and the first part of the course will be dedicated to classical questions. And another part is second part will be about neural networks, fancy things, about image restoration with neural networks, and everything you like. Yeah. First homework, I think it will be after the second seminar, when you will know more about image processing, and you will have some practice on that to apply all those things, or not all, but some of those things. GANs, I think it will be covered in our one of 3 courses on neural networks. It's an NLP, it's a CV, and it's a reinforcement learning. I think it will be one lecture on that, because GANs, it's not about neural networks, it's more like about models that generate some distribution. It's a statistical model, but neural networks shines really well, and for computer vision that's where it was created, in the same way like transformers were created in NLP, but nowadays they are applied everywhere, in computer vision, in reinforcement learning, in graphs, and everywhere. So, okay, thank you. See you next week.
Thank you very much.
Goodbye.